Hello everyone. Welcome to another data science video. In this video, we will see how to select the right input parameters for building machine learning model, or in another word, how we can choose the most effective feature in the dataset to build a predictive model for the targeted output. Here we have imported all the libraries that we might need to make this project. As we can see here, that we have imported the pipeline function, or we could import the makePipeline function instead, because they are both functionally equivalent. So, here what the pipeline function does is, takes a list of functions and squishes them into a single function. Or we can say that the pipeline function creates a sequence of steps together. For example, it can a new function combining the feature selection function, normalization function, and classification function altogether. However, in this video, we will not implement the pipeline function and all of these imported libraries in action. But we hope we will be able to see them in the next video, when we will see how to draw PCA scatter plots with appropriate categorical legends. Now, let's import the dataset. Here in this project, we will be working with the breast cancer dataset. It is a familiar dataset because in the previous video we have built a sequential model based on the artificial neural network using this dataset that could predict the target is malignant or benign. As we know that the dataset has a total of 33 columns, and it also has an empty column. The first part of data preparation is cleaning. Since the breast cancer dataset we know is already clean. Therefore, we just need to drop that empty column. Now, loading all the features from column 2 to the last column into the input parameter, x. And the diagnosis column, the column index 1, is our targeted output y. As the output, y, contains all categorical values, therefore we need to convert y into numerical values. Here using the numpy, where function, we are converting all am's to 1, and all other categories to 0. Since the target, y, contains only two categories, malignant and benign. Therefore the where function will convert all b's to 0. Or, we can transform categorical variables into numeric values using scikit-learn hot encoder. The advantage of using hot encoder is that we can use this function on multiple columns. However, it may be the topic of another discussion. Also, remember that, we could use the scikit-learn's label encoder class as well, to convert categorical variables to numeric values. Now we will see how we can select the right features for the input parameter x. So, let's find the correlation among the features of each other. Correlation measures the linear relationship between two variables. Here the matrix tells us that the extremely correlated features are doing the same thing. For example, the perimeter mean column and the area mean column. These two features are extremely correlated because their correlation is approximately 1. So, this statically means that they are doing the same thing in the dataset. Therefore we can just drop any one of them to reduce data dimensionality. Because dimensionality reduction helps the model better optimizing algorithm for overfitting and underfitting problem. Now, let's plot the correlation matrix. As we know, correlation measures the linear relationship between two variables. So if the correlation is +1, then we can say that these two variables has a strong positive relationship. So, it also means, if one of the variables increasing at a certain point, another one also doing the same, at that point. Also, if one is low at a point, the other is also low, at that point. By plotting a scatter plot we can understand the fact more clearly. As we can see in the plot, the relationship between these two features, area mean and perimeter mean, are strongly positive. On the other hand, the negative correlation tells that the two variables are totally different, therefore doing completely opposite thing. So, if one increasing at a certain point, the other one is decreasing at that point, and vice versa. The correlation function only runs on numeric data. So, before passing the data frame into the function, make sure the data frame has only the numeric values. As we can see in this plot that there are too many positive relations that exist between various features. This means these columns are particularly doing the same thing in the dataset. So we can eliminate a few of these columns when choosing features for the input parameter, x, to build our machine learning model. But we should not just find a positive correlation and eliminate the feature, because there might have an important feature that making a large impact to predict the target y. That's why domain knowledge comes in handy. It helps to select the right feature for the input parameter, x. Or the domain knowledge can also help us to decide which features we can merge into a different one. For example, the height and weight features are mutually correlated to each other positively. Therefore, we cannot just drop the height feature and choose the weight feature for input. Rather, we can merge these two features into another important feature called BMI. Because the input feature, BMI, impacts mostly for the model to predict the target, rather than height and weight individually. But, without domain knowledge, we can also find the important feature in the dataset for predicting the target, y, using scikit-learn's ExtraTreesRegressor class. It implements a meta-estimator that fits a number of randomized decision trees, also known as extra trees, on various subsamples of the dataset, and uses averaging to improve the predictive accuracy and control overfitting. Here we have created the ExtraTreesRegressor model and fit the input x and target y to the model. Now, to see all input features' contribution to the output, we have called the feature importance property on the regressor model. Here we can see the feature contribution result in percentage values. To visualize each feature that contributed to the output, y, we have plotted the result. As we can see here that the radius worst, concave points mean, etc. So these features contributed mostly to the target y. Now, we know the most important feature in the dataset. So we can just drop the extremely correlated features in the dataset that are not contributing mostly to predict the target. Here we have listed all the extremely correlated features we have found in the correlation matrix. Now let's drop the correlated features that are not the most important for the target y. So, we'll not drop those features here we have listed as mostly contributing to predict the target y, although they are highly correlated to each other. Now we have dropped some of the correlated features that are not most important for the target variable y. Let's check the correlation map again. Here we can see we have another feature, concavity mean, which is also extremely correlated to the most contributing feature, concave points mean. As the concave points mean causing a high impact to the target y, therefore we should drop the concavity mean column. Here we also have other extremely correlated features we can see on the map. But we cannot just simply drop these features, because they are the most important feature to train our model to predict the target y. Now we can think our input parameter, x, is relatively neat than before, so we can now pass this data to train our model, expecting a better and clean prediction result.